In addition to supplying various physical and logical resources, the parent process may pass along initialization data to the child process. For example, to the child process. So when a process creates a new process, two possibly for execution exist. That is, the parent continues to exist concurrently with its children. The parent waits until some of all of its children have terminated. There are also two address-based possibilities for the new process. The child process is a duplicate of the parent process. It has the same program and data as the parent. The child process has a new program loaded into it. To illustrate these differences, let's first consider the Unix operating system. In Unix, each process is identified by its process identifier, which is a unique integer. A new process is created by the fork system call, such as here, fork system call. The new process consists of a copy of the address space of the original process. This mechanism allows the parent process to communicate easily with its child process. Both processes, the parent and the child, continue execution at the instruction after the fork. Continue to execute from here if from this statement, if statement. With one difference, the return code for the fork is 0 for the new process. So if it is new process, that means the child process will, this return value is 0. If it is parent process with one whereas process identifier of the child is returned to the parent. So if it is parent process, it will get data that is larger than 0, because it is the PID paid of the child process. The parent process will get the return value, the paid of the child process, the parent process will get, okay? So, after a fork system call, one of the two processes typically use the EX, this system call, to replace the process memory space with the new program. Here, the new program is this one, okay? With a new program, the EX system call loads a binary file into memory, destroying the memory image of the program containing the EX system call. And the starts then go their separate ways. So that means though after fork system call, the child and the parent processes are the same statements, but because the child process and the parent process will catch different return value, so the child process will execute this system call and replace all the memory space by replace the data section and the text section by this program is. Okay, so then the child process and the parent process will execute separately, different. Okay, the parent can then create more children, or if it has nothing else to do while the child runs, it can issue a wait system call to move itself off the ready queue until until the child process finish its execution. So just like our example here, the parent process will issue this system call wait. It suspend itself and this system, the operating system, will put the child process into waiting queue. Waiting what? Waiting the child process to finish. After finishing this program, then the parent process will get the signal and will be scheduled into ready queue again by the operating system. And when it executes again, it will print this information on the screen, you can see, and then exit. Okay. This program illustrates the Unix system calls previously described. We now have two different processes running copies of the same program. The only difference is that the value of paid for the child process is 0, whereas that for the parent is an integer value greater than 0. The child process inherits privileges and scheduling attributes from the parent, as well as certain resources such as open file. The child process then overlays its address space with the Unix command, with this command system call. The parent waits for the child process to complete with the wait system call. When the child process finishes execution, the parent process resumes from the call to wait, where it completes using the exit system call. This is also okay.